long, long ago, in a land far, far away, Europe to be precise, two working independently and unbeknownst to each other, invented a system of mathematical analysis that became known as calculus.
Hi there, I'm Jeremy Clavens. Welcome to the candy-coated world of Calculus Part 1. Over the next 2 hours, we'll pack your brain with mounds and almond joys of calculaic knowledge and know-how, including functions, limits, continuity, derivatives, and much, much more.
Now we know that calculus can be a really rough ride at times. The Standard Deviants have scoured the nation for all the introductory calculus material you need to know, and then hired some cream-of-the-crop calculus professors to help us. You can count on us to simplify this math stuff and make it easy to learn, easy to remember, and just a little bit enjoyable. Believe it, it's our job.
Keep in mind that you've got a remote control, and once you master this remote control, you'll be able to control the speed of this calculus presentation.
So, once you get started, anytime you feel like slowing down,
speeding up,
pausing, or rewinding, and now we roll. Feel free to do so.
As you may know, if you've ever cracked open a calculus book, there are tons of formulas that get thrown at you. To help you keep all of them straight, we've included a handy insert card along with the videotape. It lists all the big formulas you'll see, so you'll have them when you need them. That's what makes it handy. The pack also contains a full outline of our course, so you'll be able to see where we are and where we're going.
Testing. Hello? Yes, can I have your attention, please? Listen up. To truly absorb the intricacies of calculus, you must attend your classes, read your books, study hard, and listen to your professors. So go to class.
Part 1. Introduction. Prepping for calculus.
Now, let's get down to business. Since you're watching this tape, you must have some form of mathematical background. The only way we can cover a lot of calculus stuff is to assume that you've got a good grasp of the basic concepts in algebra and trigonometry. Courses that you've already mastered, right?
Section A. What is calculus anyway?
Yeah, that's what I'd like to know.
Calculus. Calculus. It sounds like a villain on Batman, or perhaps a city in Missouri, but it's essentially just the mathematics of change. In the real world, things don't fit into neat little tidy packages, as many mathematical and scientific theories and formulas do. In elementary mathematics, you deal with perfect objects and formulas that are mostly found only in textbooks. Now, in calculus, on the other hand, you deal with more complex and irregular situations that come up more often in the real world.
Let's look at some examples. On the left side of the screen, you see problems for situations that algebra deals with. On the right side, you see examples of the more irregular problems or situation that calculus takes on. Algebra deals with slopes of straight lines. Calculus deals with slopes of complex curves. Algebra deals with constant speeds in motion. Calculus deals with varying speeds in motion. Algebra deals with areas of rectangles and triangles. Calculus deals with areas of weird-looking objects more apt to actually exist. So as you can see, algebra is much more regular and less real, whereas calculus is less regular and therefore more applicable to real situations.
Section B. Review time.
Here we go. We're going to fly through these. As we go along, if you feel that you need more review, be sure to check out The Adventurous World of College Algebra Parts 1 and 2 and The Dangerous World of Pre-Calculus Parts 1 and 2. The first topic we need to focus on is graphing. Graphing is essential to understanding calculus. The best thing you can do for yourself is to purchase a graphing calculator or computer software. If you're taking a course, your teacher may require or recommend a specific kind, so ask. They aren't that expensive and will save you oodles of time, so we suggest you go for it.
Here's your basic two-dimensional graph, also known as the XY graph. We'll use this all the time. The horizontal axis is the x-axis, and the vertical axis is the y-axis. This two-dimensional graph allows you to consider two separate variables and determine how they relate to one another. In other words, we're looking at how two separate variables, x and y, change in relation to each other. Graphs help us to understand the question, what happens to y when I do this to x? You can plot points on the graph for where the two variables, x and y, correspond and are related. Then you can connect the dots and draw your line or curve, whatever the case may be. I always liked connect the dots. Oh, look! A horsey!
With the basics of graphing done, we can now talk about functions.
Okay, so what do we mean when we talk about a function? Is it more than just a stuffy social event? A function is a way of relating two variables, x and y. We can describe what happens to y for a specific value of x with a function. So we say that y is a function of x, because the y value depends upon the x value. Also, there must only be one y value for each x value.
Here's an example you can relate to. The grade you get in calculus class is a function of how much you study. The number of hours you study is the x, which we call the independent variable, because how much you study is up to you, isn't it? The grade you get is the y, which we call the dependent variable, because your grade depends on how much you study. So your grade, or y, is a function of the number of hours you study, or x. Now, here's the notation for a function. The function f of x is written this way. F of x is another way of saying y, or the y-coordinate of a point. X stands for the corresponding x-coordinate, so a point on a given curve could be represented in either of two ways, xy or x f of x.
Okay, so you've got this x-coordinate, right? What you normally do with a function is find the value of f of x, or y, when your x-coordinate is equal to some number, which we'll call a. Hello, a. So, for a function, we want to find the values of f of x when x equals a number a. Finding these values enables us to draw the graph of a function. Every function can be graphed, at least approximately.
The way to graph a function is to pick a value for x and then plug it into the function and compute the corresponding y. Sometimes you only need to do this a few times. If the function is a straight line, then you only need 2 points to graph it, and maybe a third point, just to make sure that it's a straight line. Now, let's look at an example that illustrates some of this function jazz.
As you know, it's tough these days making it through college financially. Sometimes you need extra money to pay for things like miniature golf, Pop-Tarts, and shower shoes. To help make ends meet, Joey has taken a part-time job.
Hi, this is Joey at the Calculus Friends Network. How can I help you? No, I'm not a psychic. This is the Calculus Friends Network. What equation can I help you with today?
Suppose Joey earns a function that represents how much money he makes be f of x, or y, equals 5 times x, where x is the number of hours worked and y is the amount of money earned. As is often the case with functions, the x value is the independent variable, because Joey can control the amount of hours he works, and the y value is the dependent variable that results from the x we pick. Another way of saying this is that Joey's pay, y, depends on his work, x. So in our case, y is the total amount of money Joey makes for working x number of hours.
If Joey works for 2 hours, then in the equation x equals 2. To find y, or the total amount he will make from working 2 hours, substitute 2 in for x. Subbing in, we get f of 2, or y, equals 5 times 2, or 10. So Joey gets $10 for working 2 hours. Tough economy. Plot the point 210 on your graph. Substitute another value for x, such as 3 hours. We can get an f of 3 of $15, which you can also put on the graph. Then, if you simply draw the line connecting them, you get the graph of this function, which is a straight line.
The graphs of functions do not necessarily have to be straight lines. Some functions are curves, which could look like this, or this, or this. Oh, and by the way, some functions are really boring.
Take a look here at this function, f of x equals x cubed. For this sucker, you need more than 2 points to figure out what it looks like because it's not a straight line. Let's plot a few. If you substitute, let's say x equals 1, then y equals 1. Then, if x equals 2, y equals 8. And if x equals negative 2, y equals negative 8. If you keep plotting more and more points, this curve appears.
Let's look at a few more functions which you could graph. However, as we've said, the easiest way to graph these functions would be with a souped-up graphing calculator.
If you plotted enough points, this function f of x equals x squared would look like this parabola. This function f of x equals x cubed minus 4x would be graphed like this curve.
That's it for our review and discussion of functions. Remember, if you're still a little shaky, you can always rewind the tape and watch the review again. No one will know but you. Now on to the nitty-gritty.
Part 2. Limits and Continuity.
Section A. The intuitive definition of limit.
We just finished a brief discussion of functions and their graphs. Why so brief? Well, in calculus, we're beyond working with pure functions. What we're now focused on is finding the limits of these functions.
The limit is essentially finding what value f of x is close to when x is very close to a certain number called a, but not necessarily equal to a. Whoa.
The limit is essentially finding what value f of x is close to when x is very close to a certain number, called a, but not necessarily equal to a. As you can see on our graph, as x approaches this certain number a on the x-axis, the corresponding value f of x of the function approaches a certain value, symbolized here by L on the y-axis, which is the limit.
Now pay attention. Here's the notation for a limit. Wait a minute, that's the notation for a limit which we don't pay attention to. Alright, here we go. This is the notation which you'll need to remember. We read this notation as the limit of f of x as x approaches a equals L.
In many cases, finding the limit of f of x as x approaches a is the same thing as evaluating f of x at a. So the limit of f of x as x approaches a and the actual value of f of a are often the exact same thing. Now we'll do some examples to demonstrate what all this means. Section B. Actually finding the limit.
Now, on to finding the limit. Here's the function we were using earlier for Joey's earnings at the Calculus Friends Network. F of x equals 5x. Let's say we're looking for the limit of this function as x approaches 2. There are several ways to find the limit in this situation. The easiest is through a technique called substitution. Let's see how it works.
In proper notation, our problem looks like this, which reads, the limit of 5x as x approaches 2. With substitution, we simply substitute 2 in for x. By doing so, we get the limit equals 5 times 2, which is 10. So if x goes to 2, then through substitution, the limit of 5x equals 10.
Finding the limit with substitution is done exactly like finding the y value, like we did when we figured how much Joey made at Calculus Friends. Just substitute in the corresponding x. The limit of 5x as x goes to 2 is equal to 10. This means when we work about 2 hours, we'll make about $10. Try feeding a family on that.
You can visualize the limit on our graph. As x gets closer and closer to 2, the value of f of x gets closer and closer to 10, and the limit of this function is 10.
So in many cases, finding f of a and finding the limit of f of x as x gets close to a are the same thing. Thus, one of the methods for finding limits, and certainly the simplest method, is substitution.
Be that as it may, it should be noted here that substitution does not always work. But we'll talk more about that later. Now here's an example.
Let's find the limit of x squared plus 4x minus 5 as x approaches 1. We'll use the technique we just learned. Torture. Just kidding. Let's use substitution. If we substitute 1 for x, we get 1 squared plus 4 times 1 minus 5, which equals 0. So, the limit of x squared plus 4x minus 5 as x approaches 1 is 0. Once again, we see that finding the limit and finding f of 1 are the same thing.
But for some mysterious reason, math teachers make a big deal about limits possibly being different from the actual value. Why is that? Well, let's see when there can be a difference.
Here's an instance where there's a difference between the actual value of the function and the limit of that function at a certain point. Let's try to find the limit of the quantity 8x squared minus 3x, all divided by x, as x approaches 0.
If we try using substitution, look what happens. We end up with a denominator of 0. Remember the basic math rule. A fraction cannot exist with 0 in its denominator, so we can't find this limit using substitution.
This is general rule with a general rule for you. If you get stuck with a big, fat 0 as your denominator, then you cannot, I repeat, cannot, use straight substitution to find the limit.
Although straight substitution doesn't work in this case, we can, with the help of a calculator, get a sense of the right answer for the limit by substituting in numbers very close to the limiting value of x.
In our problem, let's say we substitute 1/100th in for x. It's such a small number, it's practically 0, but it's not 0. After multiplying, this would give us negative 2.92. If we went farther and used even smaller numbers like 1/1000th and 1/10,000th, we would get negative 2.992 and negative 2.9992. These values are not the limit, but they are dang close to the limit. And if we compare them, we can see that they are approaching a certain value, in this case, negative 3. Numbers in this way, we would continue to get values that get closer and closer to negative 3, but never equal it. So, we can see that the function approaches negative 3, but never quite reaches it. Kinda puts the whole concept of the limit in perspective, doesn't it?
Now that we have a good estimate of the limit, we can try another method that will let us know how close we are. So if substitution doesn't work, our other option is to panic! Or you could just try factoring the expression to see if one or more of the same factors exist in both the numerator and the denominator. If so, these same factors can be canceled out.
Any non-zero number or expression divided by itself is 1.
Looking back at our example, we need to factor the expression 8x divided by x. Lo and behold, we can factor an x right out of the numerator. The numerator becomes x times the quantity 8x minus 3. You can see where this is going, can't you? The x in the numerator and denominator can be canceled out because x divided by x equals 1. So the result is 8x minus 3, and that we can work with.
We can?
We sure can. Now substituting 0 for x, we get 8 times 0 minus 3, which equals negative 3. So the limit of the original function, 8x squared minus 3x divided by x as x approaches 0, is negative 3.
Notice that negative 3 is what we inferred earlier by substituting in numbers that were dang close to 0. So we can now see that negative 3 has got to be right.
For a clearer picture of what happened by factoring, look here. The function we started with, 8x squared minus 3x, all divided by x, looks complicated. But after factoring, it is really just the straight line 8x minus 3. The only difference in the graph of the original function and the graph of the line is that there is a hole in the graph where x equals 0, or the point 0, negative 3. Why? Because our original function, 8x squared minus 3x all over x, does not exist when x equals 0. The corresponding y-coordinate of x equals 0 is negative 3. So, the hole in the graph is at the point 0, negative 3. We show this by drawing a little circle at the point 0, negative 3.
So, even though we were able to simplify this function by factoring, we still must represent the original function in our graph. So, we leave a hole in the graph at 0, negative 3, because the original function, 8x squared minus 3x, all over x, is not defined at that point. But when we simplified the expression, we were able to substitute 0 in and get our answer, negative 3. Here, we see a very important calculus rule. If you can't substitute right away, as in this example, try simplifying the function by factoring.
Let's try a similar example. Let's find the limit of the quantity x squared minus 4 divided by x plus 2 as x approaches 1. Here, there is no problem substituting. Just substitute 1 into the equation. 1 squared minus 4 is negative 3. 1 plus 2 is 3. Negative 3 divided by 3 is negative 1. So, the limit here is negative 1.
However, what happens when we change the a value? This is the kind of stuff your professors love to pull on you.
Suppose you're asked to find the limit for the same function, but x now approaches -2. You see where this is going?
If we substitute -2 for x, we'll get 0 divided by 0, which is undefined. Now we've got a problem. Well, let's try factoring this expression. The numerator, x squared minus 4, can be factored into the quantity x plus 2 times the quantity x minus 2. X plus 2 is still in the denominator. We can then cancel the quantity x plus 2 from the numerator and the denominator. So, we now have a much simplified expression, the limit of x minus 2 as x approaches -2. Substituting -2 for x, we get -2 minus 2, or -4. So, the limit as x approaches -2 of x squared minus 4 divided by x plus 2 is -4.
Warning! Warning! To avoid brain overload, rewind tape. I repeat, rewind the tape.
Now let's have some more fun with limits.
Now, let's do another example. Let's find the limit of the square root of x minus 2 divided by x minus 4 as x approaches 4. Notice, we can't substitute 4 in for x because we'll get 0 in the denominator. To get an idea of what our answer will be, let's substitute a value for x that is close to 4 into the expression. Substituting in 4.001, we get a number very close to 0.25, or 1/4, leading us to believe that this might be our answer.
We have to flex our algebra muscles to manipulate the expression into a form that we can use. We're going to use a trick that is often used in algebra. The trick is used whenever you have an expression in the numerator or denominator that involves a square root subtracted from some number, or a number subtracted from a square root.
The trick is to multiply the function by the same expression, but with the sign in the middle changed to plus, divided by itself. This same square root plus the number is called the conjugate. The conjugate. In this case, we use the square root of x plus 2 over itself. We can do this because we aren't really changing the value of the expression. Remember, anything over itself is 1.
To complete this operation, we multiply the numerator and get x minus 4. How did we get that? Well, when multiplying conjugates, we just multiply the two first terms, the square root of x times the square root of x, and get x. Then we add the product of the two final terms, -2 times 2, which is -4. Note that the middle terms cancel out additively. So, in the numerator, we are left with x minus 4.
Now we leave the denominator as it is, so we have x minus 4 times the square root of x plus 2. It's important not to multiply out the denominator. If we multiply it out, the denominator will become a big mess, and we won't be able to cancel any factors out of it. In calculus, being simplified always means being as factored as possible.
In the denominator, we have the quantity of x minus 4 times the quantity of the square root of x plus 2. We can now cancel the x minus 4 in both the numerator and the denominator, which gives us 1 over the square root of x plus 2. So that whole conjugate trick was pretty cool, huh? Now we can substitute 4 in for x, giving us 1/4. So the limit of our original function is 1/4, which is what we estimated earlier by subbing in a value that was very close to 4.
First, there was Watergate. Then, there was Irangate. Followed by Whitewatergate, Filegate, and Indogate. And now, friends, we have Conjugate. And frankly, this one scares me most of all.
Okay, let's slow down and go over what we've learned so far about limits. The easiest way to find a limit is through a technique called substitution. Substitution just means that we plug the a value, or the number the limit is approaching, into the function and evaluate f of a. The limit is usually just the function evaluated at that value.
Now, if substitution doesn't work, like when you get a 0 in the denominator, then you need to simplify the function by factoring it and canceling factors out. In some instances, you may need to get creative with the function in order to get it into a form you can work with.
For example, we learn to multiply by the conjugate over itself when we have a square root minus a number, or a number minus a square root, in either the numerator or the denominator. Multiplying by the conjugate over itself, which is the square root plus the number, allows us to cancel some factors out and get the function into a form we can work with. So remember, if substitution doesn't work at first, see if you can manipulate the function in some way to get it into a form where substitution will work. Got it?
Section C, left and right hand limits.
Up to this point, we've been talking about limits in general.
Now we'll get more specific about the particular types of limits. For some functions, we're interested in finding their limit from one side or the other. So instead of a general limit, we're now specifying which direction the limits are coming from on the x-axis. A one-sided limit can be either a left-hand limit or a right-hand limit. To picture these, here's a graph.
Let's say that this is the graph of a function. For the left-hand limit, x approaches the particular point, or a, from the left. For the right-hand limit, x approaches a from the right. Notice that from is the important word here. They each approach from either the left or the right.
For another example, look at this dumpster. Here you've got a dumpster owned by Torso Sanitation Incorporated. The dumpster is 6 feet wide and 4 feet tall. 2 of Torso's employees are at the scene. One guy, Chuck Pavlov, is standing on top of the dumpster at the left end. The other, Sammy Toons Weber, is standing 8 feet away from the dumpster on the right.
Let's now look at this situation as a function with a graph. The origin of the graph is where the bottom left corner of the dumpster and the ground meet. Chuck is standing on the dumpster at the y-axis, and the dumpster is 4 feet tall. So, he is at the point 0, 4. Toons is on the ground, 8 feet away from the dumpster, which is 6 feet long. So, Toons is at point 14, 0. Let's say these two guys are standing on the graph of a function. The function's graph goes past Chuck to the end of the dumpster along its top, then breaks and continues along the line of the ground all the way through Toons. Even though the two parts of the line do not touch, this is still one function.
So how would we write this function numerically? Well, Chuck's part of the graph is up at the top of the dumpster at y equals 4 and comes in from the left to the end of the dumpster. Toons' part of the graph is on the x-axis at y equals 0 and comes in from the right to the end of the dumpster. The end of the dumpster is at x equals 6. So the function looks like this and is read, the function f of x equals 4 where x is less than 6 and equals 0 where x is greater than 6. Just don't get confused by this weird notation.
Moving right along. Let's say Chuck is walking from the left towards the end of the dumpster, and Toons is walking from the right towards the dumpster. Neither sanitation worker can go too far on his path. Chuck has to stop at the end of the dumpster, or he'll fall and get severe nasal abrasions. And Toons has to stop at the dumpster because, well, the dumpster's right there and it's not going anywhere. So, both get stopped where the x value equals 6.
The interesting thing in this example is that you've got two limits for this function. One from the left and one from the right. As Chuck approaches 6 from the left, the limit is 4. Why? Because Chuck is 4 feet above ground, so he's at 4 on the y-axis. He's not getting any higher or lower, but he is moving from the left towards x equals 6. But as Toons approaches 6 from the right, the limit is 0. Why? Same reason, because Toons is stuck at 0, but he's able to approach 6 from the right on the x-axis. So for this example, you use separate limits.
Here's the notation for a left-hand limit. Notice that it's got a little negative sign after the a. It's read, the limit as x approaches a from the left. As you know from Chuck and Toons, when we talk about x approaching a from the left, we're talking about the direction on the number line or graph.
The right-hand limit is the same idea as the left-hand limit, except x approaches a from the right. Notice that a has a positive sign after it. It's read, the limit as x approaches a from the right.
To go briefly back to Chuck and Toons, they would each have their separate equations for their limits. Chuck's would look like this. The limit of f of x as x approaches 6 from the left equals 4. Toons would look like this. The limit of f of x as x approaches 6 from the right equals 0.
Here's another example of when it can be important to distinguish the left hand from the right hand limit. Suppose these two celebrities, Venom Dog and Sock Snake, are touring the country with their comedy act.
So, what was your problem?
I don't understand my calculus homework.
Does your calculus homework understand you?
No.
Then maybe you two should break up.
Well, believe it or not, These two yucksters made some cash this month. Denim Dog handles all the money because Sock Snake has a compulsive shopping problem. So, Denim Dog deposits $1,000 into their bank account at 5% interest, compounded annually. By compounded annually, we mean that the interest made in a year is not deposited into the account until after the year is over. How much will these celebrities have in their account in about 1 year? Well, it depends on which direction in time you're talking about.
As time approaches 1 year from the left, or before 1 year is over, Denim Dog still has only $1,000 in his account. Even on December 31st, it's still only $1,000 because the interest hasn't been added yet. But on January 1st, when the interest is added, he now has $1,050 in his account. If he doesn't deposit any more money, then this amount will stay the same, $1,050 all year. So as time approaches 1 year from the right after the interest has been added, there's $1,050 in the account.
To put this in equation form, x would equal the number of years, and y, or f of x, would equal the amount in the account. Then the limit of f of x as x approaches 1 year from the left is $1,000, and the limit of f of x as x approaches 1 year from the right is $1,050. Do you see here on the graph how the right and left hand limits don't approach the same point at 1 year? Just remember that for a second.
So, now we've talked about both general limits and limits from the left and right. General limit looks at what point the function is approaching from both sides at the same time, while the left and right hand limits are only looking at one side. We say that a limit exists at a certain point if the limit can be found as a number at that point. So a limit either will exist or not exist at a given point. Confused? Well, here's a rule that'll bring all this stuff together.
But not a general rule.
The general limit of a function exists at a point a only if, number 1, the left and right hand limits of the function both exist at that point, and number 2, the left and right hand limits of the function are equal. Did you get that? We'll say it one more time. The general limit of a function only exists if the left and right hand limits both exist and are equal. If either one of these two categories is not met, then the general limit does not exist.
For our bank account example, the general limit actually does not exist at a equals 1 because we don't know which amount it is. From the left, the limit equals $1,000, but from the right, the limit equals $1,050. Since the left-hand limit does not equal the right-hand limit, the general limit as x approaches 1 does not exist. The left and right-handed limits themselves do exist, but the general limit does not. When a limit does not exist, we write DNE, which means does not exist.
But DNE means does not exist.
Does not exist.
Like your name on Santa's list.
Does not exist.
Like a lump of coal in your stocking.
Does not exist.
If you don't know the limits of functions, you'll be flunking.
Does not exist.
We've already seen another example of when it's important to distinguish the left-hand limit from the right-hand limit. It's the torso, guys.
The right and left-hand limits of this function are not equal at x equals 6. They're both approaching x equals 6, but they're doing it from different directions. The left-hand limit meets 6 higher up on the graph at y equals 4, so that's the left-hand limit, 4. The right-hand limit meets 6 at y equals 0, so 0 is the right-hand limit. So, as we know, this entire function does not have a general limit at x equals 6 because the limits from each side are not the same. The right and left-hand limits exist independently of each other, but the general limit does not exist because the left and right-hand limits are not equal.
Now let's do a more complicated example where we actually compute all the numbers. Suppose f of x equals the square root of the quantity x minus 4. We want to find the right and left-handed limits of the square root of the quantity x minus 4 as x approaches 4.
Why should we find this out? What's so important about this example?
Only because computing this limit is vital to the survival of our species.
Oh, okay. Well, go to it then.
First, let's work on the right-hand side. This looks easy, right? Just substitute 4 in for x and you get the square root of 4 minus 4, or the square root of 0, which is 0. Well, let's be a little careful. If we substitute a value closer to 4 but to the right of 4, say 4.0001 in for x, we get the square root of 0.0001, which is 0.01. This is close to 0, so substitution seems to work. Let's think it out anyway.
When x approaches 4 from the right, the value of x is always greater than 4, but x is decreasing as it approaches 4. So we can see that the value of x minus 4 will always be positive as x approaches 4. This is very important because we are taking the square root of this value, and we know that you can't take the square root of a negative number. Unless, of course, you live in a bizarro world. Then you could only take the square root of negative numbers.
Using substitution, we again find that the square root of x minus 4 becomes the square root of 4 minus 4, which equals 0. So the right-hand limit of this function is 0.
Now, here's where things get hairy. When x approaches 4 from the left, x is increasing towards 4, but is always less than 4. For example, if 999, then we get the square root of 3.999 minus 4, or the square root of negative 0.001. But we can't take the square root of a negative number. If we substitute any value less than 4 in for x, x minus 4 will be a negative number. This is a problem since we are taking the square root of this quantity. Remember, the square root of a negative number does not exist. You can't do it. Therefore, the left-hand limit of this function does not exist.
Since the left-hand limit does not exist, and the right-hand limit is 0, the right and left-hand limits are not equal. Therefore, the general limit of the original function as x approaches 4 does not exist, because its left and right-hand limits are not equal.
Whenever you are doing a limit problem and straight substitution gives you the square root of 0, be careful. Your problem may be like this one, and the general limit does not exist.
Okay, let's review. Now there are 3 types of limits that you'll be asked to find in class. The first one is the general limit of a function, which looks at what is happening to the function's values on both sides of a certain value a as x approaches a. This is your garden variety limit, which is written like this. The limit of f of x as x approaches a equals L. Now you also have left and right-handed limits, which look at what is happening to the function as x approaches a from either the left or the right-hand side. These limits are written just slightly different. A left-hand limit adds a little superscript minus after the a, and the right-hand limit adds a little plus like so.
Why do we bother with left and right-hand limits? Well, they help us learn more about the general limit of a function. The test to determine if the general limit of a function exists at a certain point sometimes uses left and right-hand limits. We say that the general limit of a function exists at a certain value, a, if both the left and right-hand limits exist at a and are equal. And remember, if a limit does not exist, we stamp it DNE, which means does not exist. Got it?
Section D, limits involving infinity.
Now let's look at another curious power of one-sided limits. This is a special rule that applies to one-sided limits when a 0 occurs in the denominator after substitution, but not the numerator. If this happens, then the numbers are going to infinity. The question remains whether it is positive or negative infinity. Bewildered?
Let's take an example to demonstrate how this works. We want to find the limit of 3 divided by the quantity x minus 5 as x approaches 5 from both the left and the right.
First, we'll do the right. As x approaches 5 from the right, using substitution of regular old 5, we get an expression in which we are dividing by 0, which we can't do. But, from the rule we just learned, any one-sided limit that ends up with a number in the numerator and a 0 in the denominator is approaching infinity. So, according to the rule, this limit is approaching infinity. Let's try to prove that this is the case.
To prove the truthfulness of this rule, we need to get an idea of what's happening as x approaches 5 from the right by substituting in a value close to 5, but not equal to 5. If we try 5.001, we get 3,000. If we try numbers even closer to 5, like 5.0001 or 5.00001, we get even larger positive answers.
So every time we input a number closer to the value 5, we get an even larger number as our answer. Therefore, as x approaches 5 from the right, the value is getting larger and larger, or the value is going to positive infinity. It's a circle that turns around upon itself. Hey, hey, hey! Kind of like an 8 on its side. Another way to say this is that the values increase without bound. Now these are two terms for you to become familiar with. Positive infinity and increases without bound.
So the right-hand limit increases without bound as x approaches 5. How about the left-hand limit of this expression? Here's the formula for the left again.
Well, once again, pure substitution of plain old 5 would slap us with a 0 in the denominator. Youch! Which we can't do. So, let's see if we can get an idea of what the limit is doing by substituting in some values for x. Since we are approaching 5 from the left, let's try substituting in a number close to 5 but smaller than 5, say 4.999. Here we get negative 3,000. If we try numbers even closer to 5, like 4.9999, we would get even larger negative answers. In other words, as x approaches 5 from the left, we are getting larger and larger negative numbers, or the value is going to negative infinity. Another way to say this is that the values decrease without bound as x approaches 5 from the left.
Since the left-hand limit decreases without bound and the right-hand limit increases without bound, they are not equal. Therefore, based on our rules, the general limit of the whole function does not exist.
All of this can be seen in the graph of the curve. Since x gets closer and closer to 5, but never reaches it, the line x equals 5 represents a boundary for the curve on the graph. A boundary such as this is called an asymptote. Asymptote. Because this asymptote runs parallel to the y-axis and goes up and down, it is called a vertical asymptote for the curve.
The rule holds true for functions where substitution gives you a 0 in the denominator, but a non-zero number in the numerator. So, if there's a 0 in the denominator and not in the numerator, the one-sided limit is going to be either positive or negative infinity. Subbing in a few numbers will tell you which. It's important to point out that the values of the function are approaching infinity as x gets closer and closer to 5. That's why we have a vertical asymptote at x equals 5. Let's now see what happens with the same function as x approaches infinity.
Here's another type of limit with the same function. Let's find the limit of 3 divided by the quantity of x minus 5 as x approaches positive infinity, or as x increases without bound. The only difference is that x is going to infinity or increasing without bound, and not to 5 as it did in the previous example. Again, because infinity has no specific value, to get an idea of what's happening, we need to substitute large values in for x.
Substituting 1005 in for x gives us 3 1000s. If we try numbers even larger, we get even smaller values, but still positive answers. In other words, as x approaches positive infinity, the value of the function is getting smaller and smaller, but remaining positive. So, the expression gets closer and closer to 0, but never actually reaches 0. So, the limit of the function as x goes to infinity is 0. We'll first check out this graph.
Once again, remember that f of x equals y, since the value for the expression is getting closer and closer to 0, but never quite reaches it. The line y equals 0, which is the x-axis, also represents a bound for the curve on the graph. In this case, the values of the function are not approaching infinity. As in the last case, they are approaching 0. Therefore, we have a horizontal asymptote at y equals 0. We call this boundary a horizontal asymptote because it goes across the graph, and not up and down like the vertical asymptote.
Why do we find limits as x approaches infinity? Let's see. Well, many times our function f of x is the amount of something over time x. We're interested in what will eventually happen to the amount f of x after a long period of time, or as x increases without bound.
For example, suppose that we had a function that determined the amount of salt water that leaked into a large tank of fresh water over a certain period of time. We may want to know how much salt water had leaked in after 10 or 100 or 1,000 minutes. Or we may simply be interested in what will eventually happen over time. In this case, we would find the limit as the time approached infinity. This would let us know what would eventually happen if we never fixed the leak. Does this make sense?
How can we make sense of a senseless universe?
Here's another example. Let's find the limit of x cubed plus 4 divided by the quantity of x squared plus x plus 1 as x increases without bound. Substitution will not work here because, as you know, there is no specific number for infinity. We also can't simplify the expression anymore by factoring. So to see what's happening, let's substitute a really big number in for x. Quick, give me a really big number.
Okay, 1,000. How's that sound?
575.
137. 987.
5.
14. 7.
Say x equals 1,000. Subbing in, the answer we get is about 999. As x gets larger and larger, it appears that the approximation of the limit is getting larger and larger also. So the limit may be infinity. But to truly determine this, we'll try a new algebraic trick to simplify the expression.
To get an approximate simplification of this expression that we can work with, we can use another superalgebra trick. This is a special trick that should only be used when taking limits where x is approaching infinity. We'll see why later, but first, the trick. Here's how it works.
Let's divide the numerator and the denominator by the highest power of x found in the denominator. So in our example, x squared is the highest power of x found in the denominator. We would therefore divide the numerator and the denominator by x squared.
To simplify this expression, we divide each term in both the numerator and the denominator by x squared. After simplifying, we are left with x plus 4 divided by x squared in the numerator and 1 plus 1 divided by x plus 1 divided by x squared in the denominator.
Let's look at the numerator and the denominator separately. First, the numerator. In the numerator, the second term, 4 divided by x squared, will go to 0 when x goes to infinity. Why? Based on our rule from earlier, if the denominator of a fraction, like 4 over x squared, goes to infinity, and you have a number in the numerator, then the value of that fraction produces an extremely small number, or essentially 0. So we can say that approximately any fraction with infinity in the denominator will approach 0. Since this expression is going to infinity, then, in the numerator we are left with the first term, x, plus the second term, which we just found out to be going to 0. So the numerator is now x plus 0.
Now, for the denominator, we see that 1 divided by x and 1 divided by x squared will go to 0 when we sub in, because both have infinity only in the denominator. So, putting things back together again, in the numerator we're left with x plus 0, and in the denominator with 1 plus 0 plus 0, which simplifies to x over 1, or just x.
So after all of that rigmarole, our expression is approximately x. This makes sense because when we substituted 1,000 into the original expression earlier, we got 999. And when we substituted 2,000 in, we got 1,999. So, our estimate was correct. If we take the limit of x as x approaches infinity, then our limit is infinity, because our values are approximately equal to x. We can see this by looking at the graph of the function. X is just going way, way out there.
Now that we've looked at this last example, it's time to learn a special rule about limits where x approaches infinity. You might say that this is another one of our special trick rules. Here goes. If x approaches either positive or negative infinity, and the function approaches a numerical value L, then the function has a horizontal asymptote at y equals L. Let's see how this works.
Here's an example that'll illustrate our point. Find the limit as x goes to infinity of x cubed plus x plus 1, all divided by the quantity x cubed plus 4. Again, to get a feel for this problem, let's substitute in a large number for x, say 1,000. This gives us a ballpark guess of about 1. To get the real answer, though, we'll need some more nifty algebra. First, we'll evaluate this expression by dividing the numerator and the denominator by the highest power of x in the denominator, which is x cubed.
Dividing by x cubed, the numerator becomes 1 plus 1 divided by x squared plus 1 divided by x cubed. The denominator becomes 1 plus 4 divided by x cubed. We then proceed just like the previous example.
The numerator goes to 1 plus 0 because of dividing by infinity. The denominator goes to 1 plus 0 for the same reason.
So the whole expression becomes 1 divided by 1. Therefore, the limit of the entire expression is 1. Since the limit equals 1 as x approaches infinity, this means that the line through y equals 1 is a horizontal asymptote for this function. Why do we know this? Well, that's just the special rule we learned. Since x is approaching infinity and the limit of the function is 1, then we have a horizontal asymptote at y equals 1. We can see this in the graph of the function. As you can see, the function does not move past the horizontal asymptote of 1.
And that's it for our section on limits involving infinity.
Section E, determining limits by inspection.
Well, we're almost done with the limit section. Before we go, we've got a really cool shortcut to determine some limits just by looking at them. This is also called determining limits by inspection.
Here's the shortcut we can use to determine limits by inspection. There are two conditions that must be met before we can determine limits by inspection. First, this method only applies for limits when x is going to positive or negative infinity. And second, the limit must involve a polynomial divided by a polynomial. For example, here's a problem from earlier. The limit of x cubed plus 4 all over the quantity x squared plus x plus 1 as x approaches infinity. This problem fits these two conditions because it is a polynomial over a polynomial and x is approaching infinity.
If the problem you are working with meets these conditions, then you can apply these time-saving procedures.
The key to determining limits by inspection is in looking at the powers of x in the numerator and the denominator.
Remember that to apply these rules you must be dividing polynomials, and x has to be approaching infinity. Now the first shortcut rule says that if the highest power of x is greater in the numerator than in the denominator, then the limit of the expression is positive or negative infinity. A little thought will tell you whether it's positive or negative. Would have been nice to know this when we worked those last few problems, huh?
Yeah.
Let's look at an example. The limit of x cubed plus 4 divided by x squared plus x plus 1 as x approaches infinity. Since the highest power of x in the numerator, 3, is greater than the highest power of x in the denominator, 2, the limit of this expression is either positive or negative infinity. Since all the numbers are positive and x is going to positive infinity, the limit must be positive infinity. If you can't tell easily if the answer is positive or negative infinity, you can substitute in a large number for x and see if you end up with a positive or negative number. Whatever sign you get is a sign of infinity for the limit.
Now, the second shortcut rule says that if the highest power of x is in the denominator, then the limit of the expression is 0. Look here.
Here we go. We've got the limit of x squared plus 3 divided by x cubed plus 1 as x approaches infinity. Since the highest power of x in the numerator, 2, is less than the highest power of x in the denominator, 3, the limit of this expression is 0.
Now, the last shortcut rule is a little bit trickier than the first two, so stick with me. Here goes. This rule is used when the highest power of x in the numerator is the same as the highest power of x in the denominator. If this is the case, then the limit as x goes to positive or negative infinity is just the quotient of the coefficients of the two highest powers. Remember that coefficient is the number that goes with a variable. For example, 2 is the coefficient of 2x squared, and 75 is the coefficient of 75x to the fourth. Now don't let yourself get confused over this one. Look at this example and see how easy it is.
Suppose we were inspecting the limit of 4x cubed plus x squared plus 1 all divided by the quantity 3x cubed plus 4 as x approaches infinity. Now this would be pretty doggone complicated to solve the old way, but we can put our third shortcut rule to good use here. Look. The highest power in both the numerator and denominator is 3. According to this rule, that means that the limit is just the coefficients of the x cubeds over each other. The coefficient of x cubed in the numerator is 4, and the coefficient of x cubed in the denominator is 3. So the limit equals 4 over 3, or 4/3. You see how easy that is?
Section F, continuity.
We now move to a brief discussion of continuity. Normally, we would say something is continuous if it has no breaks or disruptions. Time, for instance, is something we think of as continuous. We can tell if a function is continuous if, when we draw its graph, we never have to lift the pencil from the paper.
This is a continuous graph, and so is this. This is a kangaroo.
There are 3 conditions that must be met for a function to be continuous at a point. We can call a function, denoted f of x, continuous at a specific x value, denoted c, if it satisfies 3 conditions. First, condition 1.
The first condition that must be met for a function f of x to be continuous at a point c is that the function must be defined at the point in question. In other words, f of c must be defined. This means that when you plug the number c into the function, you get a number value. If you plug the c value in and get 0 in the denominator, then that would be an example of a function that is not defined at that point.
The second condition that must be met for a function to be continuous at a point c is the limit of f of x as x approaches c exists. This means that your function, f of x, has a numerical limit as the x value approaches a given number, c. Remember Chuck and Tunes? That was an example of a function that did not have a limit at the point where the dumpster ended.
And the third and final condition that must be met for a function to be continuous at a point c is the limit of f of x as x approaches c is equal to f of c. This means that the value of the function when you substitute in c is equal to the limit of the function as x approaches c. This is just like our straight substitutions from earlier. So continuous functions are ones with plug-in limits.
Okay, let's look at this continuity stuff a little closer. Oh, that's better. With continuity, we can determine either the continuity of a function as a whole or at a specific point. Let's test the 3 conditions for continuity with some of our old pals. Remember our puppet celebrities?
That's us!
Denim Dog deposited $1,000 in a bank account at 5% interest compounded annually. During the entire year, he only has $1,000 in his account since the interest isn't added until the end of the year. So, if we want to determine if the function is defined at half a year or 0.5 of a year, we just need to find the value for f at 0.5. The answer is $1,000 because after half a year, no interest has been added. So, condition 1 is met at half a year for this function.
If we want to determine how much is in his account after about half a year has elapsed, that would be the limit of the amount in his account as x approaches half a year, or 0.5. This is also $1,000 because no interest is added until 1 year. So condition 2 is met. Since the limit as x approaches half a year is equal to the function evaluated at half a year, condition 3 is also met, meaning that the function describing the amount in Denim Dog's account is continuous at half a year.
Hey, didn't you just visit the bank? Yeah, but it wasn't much of a visit. Why not? It couldn't hold my interest.
Now let's determine if the money in Denim Dog's account is continuous at 1 year. After 1 year, when the interest is added, there's $1,050 in the account 1 year, and condition 1 is met. Now, if we want to know how much is in there after about 1 year, which would be the general limit at 1, the answer is it does not exist, because we don't know if this refers to just before 1 year, which is $1,000, or just after 1 year, which is $1,050. This means that condition 2 is not met because the limit does not exist at 1 year.
The general limit does not exist as x approaches 1 since we don't specify which side we're coming from. Another way to think about this is that the left-hand limit is 1,000 and the right-hand limit is 1,050. Since the left-hand and right-hand limits aren't equal, the general limit does not exist. Therefore, the function is discontinuous at f of 1 because the general limit does not exist there.
Remember, the second condition for continuity said that the limit had to exist at the point for the function to be continuous there. Although both the left and right-hand limits exist, the general limit does not, because the left and right-hand limits are not equal. Let's look at the graph of this function to get a better understanding.
From the graph, we can see that the function is discontinuous at x equals 1 year, 2 years, 3 years, etc. This is because at each of these points the interest is added and the graph of the function jumps. The hole at each point indicates that it jumps up from that level to the level where the solid point is. The graph is continuous, though, at all other points of the function. So, at specific points, like at 1/2 year, the function is continuous.
Usually a curve is continuous at all points except where something unusual is happening with the function. For example, the function may have an odd disorder where it can only wear plaid. Or you may have a function like this, where f of x equals 1 over the square root of x minus 4. In that case, it would not be continuous for all values of x that will result in taking the square root of a negative number. In this example, that would be for all values of x that are less than 4.
Another situation where a function would be discontinuous is division by 0. Using the same function, f of x equals 1 over the square root of x minus 4, this function is also discontinuous at x equals 4 because that would give us a 0 in the denominator, and that's just not possible. A third instance where a function may be discontinuous is when the function is defined in a special way, such as in our case with the interest being added at the end of 1 year.
Here's another example of a function that is discontinuous at one point. F of x equals the absolute value of x divided by x.
The absolute value of a number or expression is the positive value of that particular number or expression. So memorize it. Memorize it.
See here, if we substitute -1 for x, we get f of -1 equals -1. If we substitute -2 for x, we get f of -2 equals -1. In fact, for any negative x value, the function equals -1. This means that the limit as x approaches 0 from the left is also -1, since all those f of x values are -1. If we substitute a positive value in for x, say 5, we get f of 5 equals 1. In fact, for any positive x value, the function equals 1. This means that the limit as x approaches 0 from the right is 1, since all those f of x values are 1. Therefore, the general limit of this function as x goes to 0 does not exist, since the limit from the left and the limit from the right do not give the same value. Since the limit does not exist here, the function is discontinuous at x equals 0.
If x equals 0, then we get a 0 in the denominator, which is a bad thing. So f of 0 is not defined, which also tells us that the function is not continuous at x equals 0. So for this problem, you have a choice. You could show that it is discontinuous because condition 1 is not met, because the function is not defined at 0. Or because condition 2 is not met, because the limit of f of x as x goes to 0 does not exist. Remember, if any one of the three conditions is not met, that's all you need to show that the function is not continuous at that point.
We can see that this function is discontinuous at x equals 0 by looking at the graph. You can see that the function is an unbroken line at -1 until x reaches 0, and then at 0 it breaks and moves up to 1 and continues unbroken from there. So the function is discontinuous at x equals 0, but is continuous at all other points. The graph has a step in it, so it's called a step function.
Let's look at another example. Suppose that f of x equals the quantity 3x squared plus 5 divided by the quantity x cubed plus 5x squared plus 6x. Let's determine if this function is continuous, and if not, where it is discontinuous.
So where do we begin? Well, the first condition that must be met for a function to be continuous at a point is that the function must be defined at that point. So if a function is not defined at a point, then the function is discontinuous at that point. If we can find any point where the function is not defined, then the function is discontinuous at those points. Let's see then if we can find any points where the function is not defined.
As we've seen, 0 in the denominator causes the function to be undefined and therefore to be discontinuous. So, we're looking for values of x that cause us to divide by 0. Again, notice that we're only dealing with the denominator, since it doesn't matter what the heck happens to the numerator. So, we first factor the denominator to find what values of x will cause it to be 0. The denominator x cubed plus 5x squared plus 6x factors into x times x plus 3 times x plus 2. So, when x equals 0, -3 or -2, the denominator equals 0. Therefore, at these points, the function is discontinuous.
Remember, there are three requirements that f of x has to meet for it to be continuous at a point. Since we've just found that the function is not defined at x equals 0, -3, and -2, and therefore discontinuous at those points, we do not need to go through the other steps, since we already have our answer. So, we've saved ourselves some time there.
Here's one final example. This one's kind of sneaky, so stick with us. Let's say we have the function f of x equals the quantity of x squared plus 2x minus 15, all divided by x minus 3. It's easy to see that at x equals 3, the function is not defined, since we'd get a 0 in the denominator.
So, what if your professor decided to get sneaky and redefine the function in an unusual way?
Here's what your wacky professor came up with. F of x equals the quantity x squared plus 2x minus 15 over x minus 3 if x does not equal 3, and f of x equals 8 if x does equal 3. So now f of 3 is defined. It's 8. Where did the 8 come from? Your professor just made it up as a special case. He didn't want you to look at the function and say, oh, well at x equals 3, the denominator is 0, and therefore the function is undefined there. So now that we have the strange function, let's figure out if it is continuous at x equals 3. To do this, we need to see if it satisfies the 3 conditions necessary for continuity.
The first question is whether or not f of 3, or the corresponding y point at 3, is defined. Well, this is easy. By the way we define the function, f of 3 equals 8. So f of 3 is defined. That was easy.
Second, we want to know if the limit of f of x exists as x approaches. We aren't interested in where x equals 3, but in what happens to the rest of the function around x equals 3. So, we need to look at the function where x does not equal 3, which is just the original function we started with. We know we can't use straight substitution here, so we need to try to factor the numerator, simplify the expression, and substitute into the simplified expression. So,
we can factor the numerator into the quantity of x minus 3 times the quantity x plus 5. We can then cancel out x minus 3 from the numerator and denominator. Shoo-wing! And we are left with the limit of x plus 5 as x approaches 3. With straight substitution, we see that the answer to this is 8. Therefore, the limit exists and our second condition is satisfied.
Finally, for the third condition, we need to find out if the limit of f of x as x approaches 3 equals f of 3. We just found the limit of f of x as x approaches 3 to be 8. And by the original definition of the function, f of 3 equals 8 also. Therefore, the third rule is satisfied, because the limit of f of x as x approaches 3 equals f of 3. They're both 8.
So with all 3 conditions satisfied, we can say that this function is continuous at the point x equals 3. And by the way, how did your professor know to define the function as 8 at x equals 3?
Well, your sneaky professor simply worked out the limit first and found out that it was 8.
So that double-barreled function was really just the line f of x equals x plus 5 in disguise. So, to determine whether a function f of x is continuous at a value c, there are 3 conditions that must be met. Number 1, the function is defined at f of c. Number 2, the limit of f of x as x approaches c exists. And number 3, the limit of f of x as x approaches c equals f of c. This means that the value you found for f of c in number 1 is equal to the limit you found in number 2. And that's number 3. If these conditions are met, the function is continuous at that point. If any one of these is not met, then the function is discontinuous at that point. So, try to remember these 3 conditions. That's the gist of continuity.
Part 3. The derivative.
Section A. Huh? What's the derivative?
The derivative. Just what the heck is it and why do you need to know it? We'll try to answer these questions for you and have some fun along the way. So just sit back, put your feet up, and relax. Our tour of the derivative begins with its definition. First, we'll give you informal definitions of the derivative that you can relate to. Then, we'll give you the technical definition, or the formula, and we'll work some examples. And even better, we'll show you some easy methods and rules for getting around the definition.
Calculus is all about changes in variables that affect one another. It's all about motion. Think of limits as the tool mathematicians use to determine these changes. Think of the derivative as a way to measure the changes. So very simply, the derivative is a rate of change.
Okay, get this. The inflation rate for a country is a derivative. Inflation is the rate of change of the value of money from year to year. It's not the actual increase in prices. It's a rate of change, but not the actual change itself.
Here's another one for you. The speedometer on a car is a derivative. It's measuring the distance your car travels in reference to a period of time, that is, miles per hour. So, it's the rate of change in your distance relative to time.
One more. The percentage change in population. That's a derivative. It's measuring the rate of change over a period of time in the population.
We'll work some examples of the derivative in detail later, but first we've got to get a little technical so you can understand the details.
You can talk about the derivative in terms of our peachy xy graphs. Remember the slope of a line from your favorite math or economics or statistics course? It is the rise over the run, or the change in the y values over the change in the x values. It's easy to find the slope of lines because lines are straight and they have the same slope at every point. Not so for curves.
Curves certainly throw us a curve when it comes to the slope, if you get my drift. With curves, it's more complex because they change shape at every point, which means their slope changes at every point. Simply put, the derivative gives us the slope of a curve at each point on that curve. Or even more simply put, the derivative equals the slope of a curve at a particular point.
Here's a function and graph from before. F of x equals x squared. It forms this parabola. Let's pick a point here. The clearest way to think about the derivative is the slope of the tangent line to this point on the curve, or just the slope at the point. Remember, a tangent line is a line that just touches the curve at the point. So the derivative is the slope at that point A on our graph, or you could just say the derivative is the slope of the tangent line.
What's all this business about tangent lines? Well, let's look at the graph again, but without the tangent line. Point A is the point in question, or the point we would want to find the derivative of. If you zoomed in on the point with an imaginary magnifying glass and kept zooming in farther and farther, eventually this point on the curve would appear to be a straight line sloping up in a northeast direction. By zooming in extremely far, you see that the point on the curve is essentially just a line going at a certain slope. Well, zooming out, the tangent line is equal to that zoomed line. So we can say that the derivative at a point A is equal to the slope of the tangent line at point A.
Section B, the derivative definition.
All right, we're close to the definition of the derivative. Real close, but we're not quite there. We need to let you in on a couple of notations. Okay, coast is clear. The notation for the derivative looks just like that for a function, with the addition of a little slashy dot thing after the f. That little slashy dot thing is called a prime, and the expression is read f prime of x. An alternative notation is y prime, because f of x and y are interchangeable. And finally, another way to think of it is with the notation dy over dx, meaning the change in the y's divided by the change in the x's, which is what a slope is.
Okay, we're about to give you the definition of the derivative. But first you need to follow me on this last point. This is the key to understanding what the heck a derivative really is. Remember, we said that the derivative is the slope of the tangent line at a specific point. And we remember that the slope of a line is simply the change in y values over the change in x values. Now, in order to use this slope formula, we need 2 points. For the purposes of the derivative, those 2 points are x, f of x, and x plus h, f of the quantity x plus h. Where did we get those points? Well, x, f of x, is just the starting point xy, but we are representing y with f of x. The second point is represented by x plus h, f of the quantity x plus h, where h is simply the change in x. Now we have 2 points.
Now that we have our 2 points, we can find the slope of the line between them with the slope formula. You remember the slope formula, don't you? The slope is just the change in y's over the change in x's, or, as we see here, y2 minus y1 over x2 minus x1. Now, let's take our 2 points and plug them into this formula. Our y points are f of x plus h and f of x. Our x points are x plus h and x. Now, if we put those in the formula, we get f of x plus h minus f of x over x plus h minus x. We can simplify the denominator because the x's subtract each other out. So, we are left with f of x plus h minus f of x all over h. Remember, h represents a change in x values.
Look here. If we take the new formula we just got and take the limit of that as h approaches 0, then we have the definition of the derivative. It reads, the derivative of a function f, or f prime of x, equals the limit of f of x plus h minus f of x, all divided by h as h approaches 0. So, we see that the derivative is just a slope. But if we look closer, we see that the numerator is the change in values of the function during an interval h, and the denominator is just the amount of the interval h. So, the derivative is not just the limit of a slope, it is also the limit of the change in values of f of x over the change in x, or the instantaneous rate of change.
Okay, so you're looking at the definition of the derivative and thinking to yourself, what the heck is this thing? What is this dang h? Why is this so ugly looking? Well, it's really not that bad. All it is a slight variation on the good old slope formula you used as a kid. Rise over run. Change in y's over change in x's. So hang in there, you'll get it eventually.
Everybody ready? All right, now we're going to do an example. It's probably a good idea for you to have the handy formula card that was included with your video as we go through this, just so you have the derivative definition in front of you. Just a friendly tip, because we're all about being friendly. Okay, here we go. Suppose we're given the function f of x equals 4x squared minus 8x plus 3, and we're asked to find the f prime of 2. So let's use the definition of the derivative to find it.
To solve this problem, the first thing we do is sub our x in the derivative definition. In our problem, x equals 2 because we're looking for f prime of 2. So we sub in 2 for x in the derivative definition, and we get f prime of 2 equals the limit of f of 2 plus h minus f of 2 all over h as h approaches 0. Now to complete this substitution, we need to find f of 2 plus h and f of 2. How? Easy. To get f of 2, we'll substitute 2 into the given function, 4x squared minus 8x plus 3, just as we would if we were given any x value and we're trying to find the corresponding y value. So substituting 2 for x, you get 4 times 2 squared minus 8 times 2 plus 3, which equals 3. So we've got f of 2. It's 3. In other words, we just found that the x and y coordinates for this point are 2, 3. So f of 2 will get put into the derivative formula as 3.
Now to complete the derivative formula, we need f of the quantity 2 plus h. How do we get it? Heck, we just slap it back into the original function. Every place we see x, we just plug in the quantity 2 plus h. By substituting 2 plus h for x, we get 4 times 2 plus h squared minus 8 times 2 plus h plus 3. It looks nasty now, but if we multiply it out and simplify, we are left with 4h squared plus 8h plus 3.
Now, all we have to do to get the derivative is substitute our new values for f of 2 and f of 2 plus h back into the derivative formula. So, we put in 4h squared plus 8h plus 3 in for f of 2 plus h, and 3 in for f of 2. We can't substitute 0 for h yet because we'd get 0 in the denominator. Remember, when doing limits, if you can't substitute, then try simplifying and factoring. In the numerator, after subtracting out the 3's, we can factor an h out and cancel the h's in both the numerator and the denominator. Now we can substitute 0 for h. That gives us f prime of 2 equals 8. So, after all that, the derivative of f of 2 is equal to 8. So, for the point 2, 3, which is the point on the function we just found the derivative for, we know that the slope is 8, because the derivative is the slope at that point on the curve.
We've just found the derivative at a particular point on the function using the definition. Repeating that mess of computations for other x values would be tedious at best. So let's find a general formula for the derivative of our function. That way, we could find the derivative for any value of x on this function a lot quicker.
Now let's find that general formula for the derivative. Back to the derivative definition, which you see here. Now instead of evaluating for a specific point, we will sub in the full generality. We know what f of x is because we were given it originally, and f of x plus h is just found by substituting the quantity x plus h in for x in the original function. So, f of x plus h equals 4 times x plus h, quantity squared, minus 8 times x plus h plus 3. When we multiply this out and combine terms, we get f of x plus h equals 4x squared plus 8xh plus 4h squared minus 8x minus 8h plus 3. Whew, easy for me to say. If we stick these values for f of x and f of x plus h back into the derivative definition and simplify, we will get the general formula for the derivative at any point on this function.
Here we go. Subbing in our f of x and then our f of x plus h, here's what we get. Now we've got to do all the math. After simplifying, we get 8xh plus 4h squared minus 8h all over h. Again, we can't determine this limit by straight substitution because we would get a 0 in the denominator. So we factor out an h in the numerator and then cancel out the h in both the numerator and denominator. We're left with the limit as h approaches 0 of 8x plus 4h minus 8.
Now we're back in the limit world. Substitute 0 into the expression for h, because based on the original derivative formula, h is always approaching 0. This gives us 8x minus 8.
So, at any value for x, the general formula for the derivative of this particular function is 8x minus 8. To find the derivative at any point, just substitute that value for x into this formula. For example, at the value x equals 3, the derivative would be 8 times 3 minus 8, which equals 16. So, the slope of the tangent line at x equals 3 of the function 4x squared minus 8 is 16.
Okay, let's go back over this derivative stuff, starting with the definition of the derivative. The definition of the derivative is just a big formula that looks like this. The derivative of a function, f of x or f prime of x, equals the limit of f of the quantity, x plus h minus f of x, all divided by h as h approaches 0. Remember, the derivative gives the slope of the tangent line to the curve at any given point.
We use this big hunk of a definition for two things. First, to actually find the derivative at a given value of x, and second, to find a general formula for the derivative of a function. We won't go into more detail now, but remember, you can always rewind the tape if you need more review.
Now that we've learned how to find derivatives, here's a fun term that you can begin using. The term is differentiable. A function is differentiable at a point if it has a derivative at that point. An entire function is differentiable if it has a derivative at every point in its domain. So we can use the term differentiable to state that we're able to find the derivative for a certain function at a point over an interval or over an entire domain.
In our previous example, we found that the function f of x equals 4x squared minus 8x plus 3 is differentiable at the point 2, 3, because we were able to find the derivative at that point, which was 8. In fact, we found that its derivative at any point x is 8x minus 8. So this function is differentiable, meaning it has a derivative at every point.
As an extension to that, one other thing you should know is that if a function is differentiable, then it is also continuous. So differentiability implies continuity. This is true for a point, an interval, or an entire function. Now be careful, because the opposite is not always true. If a function is continuous, that does not necessarily mean that it is differentiable. But, and this is really cool to know, if a function is not continuous at a point, then it is not differentiable at that point.
One other thing you'll face in your classes is finding the equation of the tangent line after you've found the derivative. We already know that the derivative gives the slope of the function at a particular point. So it's not very difficult to determine the equation of any tangent line.
First, in order to do this, you need to remember the point-slope formula for a line from geometry. The point-slope formula for a line says that only the slope and one point on the line are needed to get the equation for that line. M represents the slope, and the point is x sub 1, y sub 1, because we need to be left with the plain old x and y in the equation. Now let's work a quick example.
If you're given a point 6, 8 and a slope of 1/2, just plug in the numbers. Y minus 8 equals 1/2 times the quantity x minus 6. The right side becomes 1/2 x minus 3. Then adding 8 to both sides, we're left with y equals 1/2 x plus 5. That's the equation of the tangent line at the point 6, 8.
Now back to the function we were working with. 4x squared minus 8x plus 3. Earlier, we found that f prime of x, or the general formula for the derivative of the function, was 8x minus 8. Now we can use the point-slope formula to get the equation of the tangent line. Suppose we want to find the equation of the tangent line to this.
To get the equation of the tangent line, we need two things, the point of tangency and the slope of the line. The point's easy. Just plug 2 in the original function. If x equals 2, then f of 2 simply equals 4 times 2 squared minus 8 times 2 plus 3, which equals 3. So the point of tangency is 2, 3.
Now we just need the slope of the line. Well, the slope is equal to the derivative at that point, so the slope of the tangent line equals the derivative of the function at the point x equals 2. Our derivative equation was 8x minus 8, so plug in 2 for x and you get 8 times 2 minus 8, which equals 8. So the slope of the tangent line at that point is 8.
Now, we have a point, 2, 3, and the slope of the line, 8. We just have to plug these into the point-slope formula to get the tangent line. So, we have y minus 3 equals 8 times the quantity x minus 2. Simplifying, we get y equals 8x minus 13. So the equation for the tangent line at x equals 2 is y equals 8x minus 13.
So, quickly, here's how to find the equation for a tangent line. The key here is to remember the point-slope formula for a line from geometry. With this formula, we can find the equation for the tangent line if we know only a point on the line and the slope of the line. In calculus speak, if we are given a function, we can find the equation for the tangent line at any value of x. The first step is to find the point on the line. To do this, for any given x, we just sub that value back into the original function to get the corresponding y. We now have a point, x sub 1, y sub 1.
Step 2 is to find the derivative of the function. We know how to do that, don't we? And then step 3 is to find the slope. You do this by subbing your x into the derivative. That will give you the derivative at that point. And we know that the derivative is the slope of the tangent line at that point. You now have a point and the slope of the tangent line at that point. And the last step, step 4, is just plug all this into the good old point-slope formula. And there you have it, the equation of the tangent line.
Section C.
All right, now we've got some important rules of differentiation or for finding the derivative. See, we use the big words we teach you. There's a plus and a minus here. First, the minus. The minus is that you just have to memorize these rules. Now the plus. It's a big plus. Wow. The big plus is that once you learn these rules, you won't have to deal with that really long derivative definition again. Unless, of course, your professor makes you for a test or something. But remember, you can always rewind if you need to.
Testing. Did it sound? Okay.
May I have your attention, please? All of the following rules will appear on the standard deviance insert cards which come with your video. So, keep them handy.
Hi, I'm an unemployed hardware salesman. I'm here to present some practical examples that'll help you learn calculus. I do this from time to time, partly to amuse myself, but more importantly, to help you remember some really important concepts. And who better to do that than an unemployed hardware salesman? Take this birdhouse, for instance. When you're working on a delicate project such as this, choosing the proper tool can be a little tricky. Now with calculus, you've got a lot of rules for finding the derivative. Think of it this way, rules are like tools. Which one you use depends on the type of problem you've got. Let's look at a few now.
The first rule you need to know is the simplest.
And the most powerful!
You will use this rule all the time. It's called the power rule. The power rule deals with any variable raised to a power, like x squared, for example. F of x equals x to the n, then the derivative of f of x, or f prime of x, equals n times x to the n minus 1. In other words, the derivative of a variable, x, raised to the power n, is n times x raised to the n minus 1 power. For example, suppose f of x equals x squared.
As you can see, n, or the exponent, equals 2. Then the derivative is just n times x raised to the n minus 1. So, the derivative of x squared is just 2 times x raised to the 2 minus 1, which equals 2x raised to the 1, or just 2x. That's it.
This rule works for simple terms, like x squared, or for expressions that have multiple terms and are a little more complicated. Let's look at an example of an expression with more than one term. Let's find f prime of x if f of x equals 4x cubed minus 8x plus 5. We could put this in that big old derivative definition formula, or we could just use the power rule. You'll soon see why the power rule will become your best friend. Now, we simply apply the power rule to get the derivatives.
Looking at the first term, 4x cubed, n equals 3 because x is raised to the third power. So the derivative is just 3 times 4x raised to the 3 minus 1 power, which is 3 times 4x squared, or just 12x squared. Don't let the d over dx notation confuse you. That's just another notation for taking the derivative of what follows. D over dx followed by f of x is the same thing as f prime of x.
Take the next term, 8x. This is 8x raised to the first power. Here, n equals 1, so the derivative equals 1 times 8x raised to the 1 minus 1 power. This is just 8x raised to the 0 power. If you remember, anything raised to the 0 power equals derivative is equal to 8 times x raised to the 0 power, which is just 8 times 1, or 8. This makes sense since the slope of the line y equals 8x is 8. Remember the slope-intercept form of a line? Y equals mx plus b, where m is the slope? Well, if y equals 8x, then 8 is the slope of that line. And that's what we just found for this term, 8x.
The last term is 5, and the derivative of any constant is 0. This is because in terms of graphing, constants are horizontal lines, and no slopes. So taking the derivative of a constant is the easiest thing you can do. So remember, the derivative of any constant is 0.
We now have the derivative of each of the three terms in this expression. The d over dx just shows that we took the derivative of each term individually. Now, we just have to combine them, and we have the derivative of the entire expression. So, in our example, f prime of x equals the derivative of the first term minus the derivative of the second term plus the derivative of the last term. So the derivative of 4x cubed minus 8x plus 5 equals 12x squared minus 8 plus 0, or just 12x squared minus 8.
So that's rule number 1, the power rule. Put that one in your tool belt. You'll definitely need it later. It's a biggie. It's like a hammer. Now, here's a couple of cases that go along with the power rule. Don't let them throw you. Just think of them as, well, splinters.
Warning! Here's an exception to the power rule for you. The power rule works only when the exponent is a number like 2, 1/2, 8, pi, remember pi, or whatever number. But you can't use the power rule when the exponent has a variable in it, such as x to the 2x. If this is the case, then another rule must be used. We won't go into that now, but just remember this exception to the power rule.
Let's look at one situation that you may encounter which has an x as an exponent. It involves a number called e. E is one of those numbers like pi that goes on forever. Here's an approximation. You can see why we call it e instead of writing it out. It represents a fixed value 2.718 ... which for some strange reason comes up all the time for mathematicians in the real world.
The rule here is, if f of x equals e to the x, then f prime of x equals e to the x. So e to the x is its own derivative. Notice that you did not multiply by the power and you did not subtract 1 from the power. The derivative of this particular function is merely equal to itself. This is an odd case.
We put it here just so you are aware of it when it comes up in your class, which it most likely will. Just in case you were wondering what E is. E is a dangerous space weapon. Actually, E is the positive real number such that the natural log of E equals 1.
So E is the positive real number such that the natural log of E equals 1. Awesome.
But you don't need to remember that. Just thought you might like to know.
Thank you for baiting me.
Another special rule, like the one we just talked about, involves natural logarithms, or as their friends call them, natural logs. Okay, there's this great joke.
No bathroom jokes, please.
Okay, here's the rule. If the function f of x equals the natural log, or ln of x, then its derivative, or f prime of x, is 1 over x.
If the function f of x equals the natural log of x, its derivative, or f prime of x, is 1 over x.
The natural log contains no additives or preservatives and was grown in accordance with the organic growers of America. When purchasing logs, look for the symbol and you can be sure you are purchasing the very best natural log for your family. Paid for by the natural log growers of America.
Let's review. First, the power rule. If f of x equals x to the n, then f prime of x equals n times x to the n minus 1. Next, the e rule. If f of x equals e to the x, then f prime of x equals e to the x. And finally, the natural log rule. If f of x equals the natural log of x, then f prime of x equals 1 over x.
Another rule to make the derivative easier to find is called the product rule. It says that if f of x is the product of two functions, g of x and h of x, then the derivative of f of x is the derivative of the first times the second, plus the derivative of the second times the first. So remember, the derivative of a product is not the product of the derivatives. It's not that simple. But if you can remember this formula, it's not that bad. Again, this is on the handy formula card you got with the video. If you haven't lost, burnt, lent, flushed, or eaten it, pause the tape here, pull it out, and follow along. Now let's look at an example.
We want to find the derivative of the quantity 3x squared plus 5 times the quantity 7x minus 4. So, to use the notation of the product rule, g of x is 3x squared plus 5, and h of x is 7x minus 4. Now, the first step is to find the derivative for each function, g of x and h of x. Taking the first function, g of x, we'll use the power rule to find its derivative. Take the first part of the first function, 3x squared. The derivative of 3x squared is 2 times 3x raised to the 1, or 6x. Now take the second part, plus 5. The derivative of 5 is 0 because it's a constant, and the derivative of all constants is 0. So g prime of x equals 6x plus 0, or 6x.
Looking at the second function, h of x equals 7x minus 4, the derivative of 7x is 7 times x raised to the 0, or 7 times 1, which is 7. The derivative of 4 is 0. So, the derivative h prime of x is 7 minus 0, or 7.
Now, let's line up what we've got here. Our original function was the quantity 3x squared plus 5 times the quantity 7x minus 4. So, g of x is 3x squared plus 5, and h of x is 7x minus 4. We just found the derivative of the first function, g prime of x, to be 6x, and the derivative of the second function, h prime of x, to be 7. Now, all we have to do is plug these into the formula. Plugging in, we get f prime of x equals 6x times the quantity 7x minus 4 plus 7 times the quantity 3x squared plus 5. This is your answer using the product rule. However, if your professor wants you to multiply it out, then you'd get 63x squared minus 24x plus 35.
So that's the product rule. Just another tool for your tool belt. It's a very important rule, but not as important as a hammer. It's like a screwdriver.
Another important rule you need to learn is called the quotient rule. The quotient rule states that if f of x is the quotient of two functions, then the derivative of f of x is the derivative of the numerator times the denominator minus the derivative of the denominator times the numerator, all divided by the denominator squared. Whew, that looks complicated, but it's really not that bad. The hardest part is to get that slippery minus sign in the right place.
Let's just use the same functions for g of x and h of x as we used in the last example. This time, though, we're trying to find the derivative of f of x equals 3x squared plus 5, all divided by 7x minus 4.
Again, the derivatives of each of the two functions, and then plug them into the formula. We know from our last example that the derivative of g of x is 6x, and the derivative of h of x is 7.
Now all we have to do is stick these values into the formula and simplify.
We get 6x times the quantity 7x minus 4, minus 7 times the quantity 3x squared plus 5, all divided by 7x minus 4, quantity squared. This is your answer using the quotient rule. Again, though, if your professor wants you to multiply it out, you'd get 21x squared minus 24x minus 35 all over 7x minus 4, quantity squared.
Okay, now you've got the quotient rule to add to your tool belt. It's kind of a complex rule, you know, like a monkey wrench. So now you've got a hammer, a screwdriver, and a monkey wrench. Who could ask for more? You're all set to tackle just about any problem.
If y equals x cubed divided by 3 plus 4x squared minus 6, let's find the derivative of y, or dy over dx.
Well, let's try a hammer on this one. Remember that the good old power rule allows us to take the derivative of each term separately. So we'll find the derivatives of x cubed over 3, 4x squared, and 6 separately. Then we'll put them back together.
Let's begin with the first term, x cubed divided by 3. Some hasty people will try to use the quotient rule here, but don't use a monkey wrench where a hammer will work better. It's much easier and quicker to find this derivative if we just rewrite it. X cubed over 3 can be rewritten as 1/3 times x cubed. Written this way, we can now use the power rule on this term. It's the same expression, just written a little differently, and much easier to work with.
Now we can use the power rule on this term, which is definitely the easiest rule to use. Remember, the power rule says to multiply the exponent times the expression and subtract 1 from the exponent. So we get 3 times 1/3 times x raised to the power of 3 minus 1. This gives us 3 times 1/3 x squared, which is just x squared.
The next term in the function is 4x squared. The derivative of 4x squared is 2 times 4x raised to the power of 2 minus 1. This equals 2 times 4x, which is 8x.
The last term in the function is 6. If you remember from before, the derivative of any constant is 0, so the derivative of 6 is 0.
Now put all these terms together to get the derivative of the original function y equals x cubed divided by 3 plus 4x squared minus 6. The answer is y prime equals x squared plus 8x minus 0, which is just x squared plus 8x. And that's a pretty fancy birdhouse if you ask me.
Nice work there, gang. You're certainly getting the hang of it. Now here's a chance for you to use another tool. I don't need this.
Here goes. Let's say we've got f of x equals e to the x times the quantity 6x cubed plus 4x plus 3. Find f.
For this problem, we'll use our screwdriver, the product rule, because we have two functions being multiplied together. Now remember, the product rule says if f of x is the product of two functions, then f prime of x is the derivative of the first times the second, plus the derivative of the second times the first.
To fit the mold of the product rule, we'll let g of x equal e to the x and h of x equal 6x cubed plus 4x plus 3. So first, we need to find the derivatives of g of x and h of x.
For g of x, the derivative is just e to the x. Remember, we learned that earlier. So g prime of x equals e to the x.
Next, we need to find h prime of x, or the derivative of 6x cubed plus 4x plus 3. Use the power rule. The derivative of 6x cubed is 3 times 6x squared, or just 18x squared. The derivative of 4x is 4, and the derivative of 3 is 0. So, h prime of x equals 18x squared plus 4 plus 0, or plus 4.
Now we have everything we need to solve this problem. We have identified our g of x and h of x, and then we found g prime of x and h prime of x. All we need to do now is gently place the values we found into the good old product rule formula here, and we will have our answer.
Gently placing in, we get e to the x times the quantity 6x cubed plus 4x plus 3 plus the quantity 18x squared plus 4 times e to the x. So, believe it or not, that's your answer using the product rule. In calculus, it is always nice to factor out any common factors and combine the remaining garbage. So let's do it. This leaves us with e to the x times the quantity 6x cubed plus 4x plus 7. It's not a bookcase, but it sure is a nice-looking wooden Tower of Doom.
Well, I hope this clever tool analogy has helped you remember all these different rules. Remember these rules/tools and you'll be just fine. Take it from me, an unemployed hardware salesman.
Derivatives.
Right, and away we go. Now it's time to hobnob with the upper-class derivatives. We call these derivatives higher derivatives because they always get the best tables in all the shishi restaurants.
Actually, a higher derivative is what you get when you take a derivative of a derivative. Look here.
Let's say we have a function f of x. When we take its derivative, we form a new function, f prime of x. This is called the first derivative of f of x. We can then take the derivative of this derivative. This would give us the second derivative of f of x and is denoted by adding another prime to our original notation. f double prime of x. Functions have more than one derivative. These are just called higher order derivatives. So to get the second derivative of a function, just take the derivative of the first derivative. To get the third derivative, just take the derivative of the second derivative, and so on.
For second derivatives, we already said that we write a double prime mark. It's read as f double prime of x. The other notations you can use for the second derivative are y double prime and the second derivative of y with respect to x, which is written out as d little 2y over dx little 2. Those little 2's are there to represent the second derivative. Make sure you put those little 2's in the right place.
For third derivatives and higher, we put the number of the derivative we are taking in parentheses as a superscript instead of using prime marks.
Let's find the second derivative of a function whose first derivative we have already determined. The function is y equals x cubed divided by 3 plus 4x squared minus 6. We have already determined the first derivative of this function to be x squared plus 8x.
To get the second derivative, we first find the derivative of this expression, which is the first derivative. Taking the expression term by term and using the power rule, you can see that the second derivative is equal to 2x plus 8.
If we wanted to find the third derivative, we would merely take the derivative of the second derivative.
Using the power rule again, 2x becomes 2 and 8 becomes 0, because the derivative of any constant is 0. So 2 plus 0 is 2. Then the third derivative of this equation is 2. You got that?
Section E, the chain rule.
So now that you've figured out how to compute derivatives, let's dig in a little further. Remember how we told you that derivatives signified change? Derivatives measure the rate of change of y as x changes.
You can see it on this graph of f of x equals x squared. If f of x equals x squared, then based on the power rule, f prime of x equals 2x. At the point x equals 1, f prime of 1 equals 2 times 1, or 2. This means that at this point on the curve, the y value is changing twice as fast as the x value.
Now here's a story to make this a little clearer. Once upon a time, there were 3 gears.
There was a papa gear, or the x gear, a mama gear, or the u gear, and a baby gear, or the y gear. The papa gear has a radius of 6, the mama gear has a radius of 3, and the baby gear has a radius of 1. Because the papa gear has twice the radius of the mama gear, each time the papa gear turns around once, the mama gear turns around twice. So we could say that mama gear, u, turns around 2 times every time papa gear, x, turns around once. So, in derivative language, the derivative of u with respect to x is 2, meaning the u gear turns around twice as fast as the x gear.
Now let's compare the mama, or the u gear, and the baby, or the y gear. Because the mama gear has 3 times the radius of the baby gear, each time mama gear turns around once, the baby gear turns around 3 times. So again, we could say that the baby gear y turns around 3 times every time the mama gear turns around once. So in derivative language, the derivative of y with respect to u is 3, meaning the y gear turns around 3 times as fast as the u gear.
Now let's look at what happens when we turn the papa or x gear. The papa gear turns the mama gear, which turns the baby gear. Now, in order to determine what the derivative of baby with respect to papa is, or dy over dx, we need to determine how many times the baby or y gear turns around when we turn the papa or x gear around once. dy over dx means how does the y gear change with respect to the x gear.
As papa turns around once, it turns mama or u around twice. And each time mama turns around once, it turns baby or y around 3 times. So, for each turn of papa, or x, baby, or y, turns around 2 times 3, or 6 times around. So, dy over dx equals 6. This is an example of the chain rule. As papa x changes, there is a chain reaction going through mama u, causing baby y to change. The chain rule says that the change in baby y, or the derivative of y with respect to x, is the product of the changes, or the derivative of y with respect to u, times the derivative of u with respect to x.
In our gear example, this means that the derivative of the baby gear y with respect to the papa gear x can't be determined directly because the x and y gears are not touching each other. However, Because the mama gear, u, is in the middle of these two gears, we can find the derivative indirectly. We do this by multiplying dy over du, or the derivative of the baby gear with respect to the mama gear, times du over dx, or the derivative of the mama gear with respect to the papa gear. See the formula here. dy over dx equals dy over du times du over dx, or 3 times 2 equals 6.
I know it's confusing keeping track of all the dy's and du's and dx's, so let's review it again before we go through an example. dy over du says that baby y gear turns 3 times if mama u gear turns once. du over dx says that mama u gear turns twice when papa x gear turns once. And dy over dx says that baby y gear turns 6 times if papa x gear turns once. How do we get this 6? By applying the chain rule and multiplying the dy over du times the du over dx.
Y over dx notations instead of the y prime or f prime of x. Why? Because it'll remember way u
and y equal u cubed. This is like our gear example because
gear or y.
Now, let's find the derivatives of mama u and baby y. Du over dx and dy, which is the derivative of y with respect to x. Thinking back to our gear example, dy over dx is the derivative of the papa gear with respect to the baby gear. So dy over dx is just 3u squared times 3, or
point out is the mama value u to get your baby value y with respects becomes 9 times x. Professor will most likely expect you to put your final answer in terms of the original function that you are finding the derivative of. In this case, that was papa x. So we want now let's
find the derivative of the square root of the quantity 2x squared plus 1.
Because of the square root, this problem looks a bit daunting. However, you can do a neat trick to make it power. Why can we do this? Well, believe it or not, the square root is equivalent to raising the quantity to the 1/2 power. It's just something that you'll need to know. This is very helpful because now we're able to apply both the power rule and chain rule to solve this problem. Just watch.
First, we're going to use the chain rule. How so, you ask? There's only one function there. Well, watch and learn, my friends. This is the beauty of the chain rule. Let's look at our function, 2x squared plus 1.